In this video, I am going to discuss about potential energy of a charged conductor. In the previous video, already I have discussed that when a conductor of capacitance C is given a charge Q, then it acquires a potential, suppose V, then Q is equal to CV or V is equal to Q by C. It means if a conductor of capacitance C, when a charge Q is given to it, then it acquires a potential V, and that potential V is given by V is equal to Q by C. And the work done in charging the conductor is stored as potential energy in the electric field in the vicinity of the conductor. Already, suppose the potential on that conductor is V, and further, when we want to give a charge dq to that conductor, then for that purpose we will do the work, and that work done, small work done, dw is equal to V into dq. It means when a charge dq is further given to that conductor, then for that purpose the work done is given by dw is equal to V into dq. By definition, you know, or dw is equal to, at place of V, Q by C into dq. This one is work done in charging the conductor by giving a small charge dq. But our aim is to find the work done in charging the conductor from uncharged condition. Uncharged condition means when Q is equal to 0 to finally a charge Q. So the work done in charging the conductor from 0 to Q. 0 to Q means earlier when the conductor was uncharged, and finally what amount of the charge is given to it? Finally you want to give the charge Q. So for this purpose, what is the total work done? For this purpose we will integrate it within the limit 0 to Q. So whole work done to charging this conductor from 0 to Q, dw is equal to 0 to Q, and here Q by C into dq. As you know, integration of dw is equal to, since the capacitance of the conductor 1 upon C, take outside, and here you will get 0 to Q into Q dq. Or W is equal to 1 upon C integration of Q dq. Like integration of x dx, already I have discussed integration of x dx is equal to x square by 2. In same way, integration of Q into dq is equal to Q square by 2, and here limit is 0 to Q. And now you can say take this 2 outside, so you can write 1 upon 2C, and here Q square limit 0 to Q. And now this work done W is equal to 1 upon 2C, and now first at place of Q you will write the upper limit, so this becomes Q, and here whole square, minus again at place of Q you write the lower limit 0, so 0 square, and finally you will get here Q square by 2C. So this work is stored in the form of the electric potential energy in the conductor. So that work done be also denoted by U, which is electric potential energy, and which is equal to U is equal to Q square by 2C. But you know Q is equal to CV. So also you can write here that electric potential energy U is equal to C square V square upon 2C, and now one C is cancelled by this one, and here you will get half CV square. So electric potential energy stored in the conductor is given by either U is equal to q square by 2c, and which is also equal to half cv square. So this is the electric potential energy stored in a charging the conductor. And when you will draw a graph, suppose when you will draw a graph between electric potential energy U and Q. So here U is directly proportional to Q square. So its nature of graph will comes like this. And when you will draw a graph between U and V, here U, electric potential energy U, and electric potential V. So here U is also proportional to V square. So its nature will be also comes like this here. So in this way you can also draw the graph between electric potential energy and charge Q, or electric potential energy and potential V. Now the next topic is redistribution of charges or common potential. Suppose two insulated conductor A and B of capacitance C1 and C2 are given a charge Q1 and Q2 and raised to potential V1 and V2. Then for first conductor A, you can write Q1 is equal to C1 V1, and for second conductor we can write here Q2 is equal to C2 V2. It means two conductor A and B having capacitance C1 and C2 given a charge Q1 and Q2, so their potential be raised V1 and V2. Then for first conductor A, Q1 is equal to C1 V1 and Q2 is equal to C2 into V2. Now if both conductor be joined through a thin conducting wire, then charge starts to flow from higher potential, means positive charge start to flow from higher potential to lower potential till their potential becomes equal. And when their potential becomes equal, that potential is called common potential. Common potential means when their potential becomes equal. Suppose V1 is greater than V2. It means potential of the conductor A is greater than the potential of the conductor B. And when both conductor A and B are connected through a thin conducting wire, then positive charge start to flow from A to B till their potential becomes equal. And that potential is called common potential. So the expression for this common potential V is equal to total charge upon total capacitance. Or we can say here, after redistribution of the charge, when both conductor acquire the common potential V, then expression for that common potential V can be obtained by using this formula. V is equal to total charge. Total charge means charge on both, sum of the charge on both conductor, which is equal to Q1 plus Q2 upon total capacitance of these two conductors, which one is C1 plus C2. And now, as you know, at place of Q1 we can write C1 V1. So C1 V1 plus C2 V2 upon C1 plus C2. This is the expression for the common potential in the redistribution of the charges. Or when two conductors which is lies at the different potential be joined through a thin conducting wire, then charge start to flow from higher potential to lower potential till they acquire a common potential, and that common potential V is equal to C1 V1 plus C2 V2 upon C1 plus C2. And after redistribution, after the sharing of the charge, now the charge on this one is not Q1 or the charge on B is not Q2. now both conductor we acquire the new charge, and the ratio of that new charge are suppose after redistribution the new charges on A is suppose Q1 dash and the new charge on B is Q2 dash. Already Q1 dash and Q2 dash when acquired by this conductor A and B, then both acquire the common potential, and that common potential already I have given the formula for that. So new charge Q1 dash on the conductor A can be obtained. Q1 dash is equal to capacitance is C1 and now it acquires the potential V. So Q1 dash is equal to C1V, and similarly the new charge on the conductor B is given by Q2 dash is equal to C2 into V. And then the ratio of the new charge after redistribution Q1 dash upon Q2 dash is equal to C1V upon C2V, which is equal to C1 upon C2. That is, on connecting two charge conductors, the redistributed charges on them are in the ratio of their capacitance. It means Q1 dash upon Q2 dash is equal to C1 upon C2. And in this process, now a question arises, what amount of the charge is transferred from one conductor to another conductor? Now in this redistribution of the charges, what quantity of the charge transferred from one conductor to other conductor? Suppose before joining, the conductor A has charge Q1, which becomes Q1 dash after A is joined with B. Thus, the charge transferred from A to B is given by Q1 minus Q1 dash. This is the charge transferred from A to B. And Q1 minus Q1 dash, as you know, Q1 is equal to C1V1 and Q1 dash is C1V. And here take C1 common. We can get here V1 minus V. And now this is equal to C1. At this of this one is V1 minus V is common potential acquired by both conductor A and B, and expression for that common potential C1V1 plus C2V2 upon C1 plus C2. And finally you will get here C1, and when you will take the LCM C1 plus C2, here you will get C1V1 plus C2V1 minus C1V1 minus C2V2 upon C1 plus C2. Now here C1V1 and here minus C1V1, both be cancelled. And you will get here this is equal to C1 and here C2V1 minus C2V2 upon C1 plus C2. Or finally we can say the amount of the charge transferred from one conductor to other, means from A to B, is given by C1 and here C2V1 minus C2V2, take C2 common, so C1 C2 in bracket V2 minus V1 upon C1 plus C2. So by using this expression we can find what amount of the charge be transferred from one conductor to other conductor. And the loss of energy in the redistribution of the charge. When charge flows from a conductor at higher potential to conductor at lower potential, then the total potential energy decreases, and that loss of energy in this transfer of the charge or the loss of energy in the distribution of the charge is given by, simply we can say here, loss of energy is equal to C1 C2 upon 2 C1 plus C2 and bracket V1 minus V2 whole square. And by using this relation, we can find out the loss of energy in redistribution of the charges. And since V1 minus V2 whole square, this quantity B always comes positive. Either V1 is less or more, it's not matter. Since this quantity B always positive, so overall loss of energy B comes positive. It means in the sharing, or simply you can say in the redistribution of the charges, always there will be the loss of energy takes place, which can be calculated by using this formula. So today all of you go through all these derivations which I have given related to this topic, and in the next video I will give the next topic. Thank you.